Hi guys, welcome to Unit 6, the continuation of Notes B. Next we're going to get into a little more details on the rate law. Keep in mind that the purpose of writing a rate law is to show how rate is dependent on the concentration of the reactants. There are two details about the rate law that was not covered in the Honors Chem notes. One is that there are actually two types of rate law, and the other thing we need to discuss are there actually are units for the rate law constant. So the two types of rate law are a differential rate law, which is actually the kind that we have been doing, so we've just been calling it the rate law. But the other type that exists is called the integrated rate law, and this shows how concentration is dependent on time. Keep in mind that rate and time are related. They are inversely proportional. If something has a fast rate, it takes a little bit of time, and vice versa. But the differential rate law is focusing on rate, and the integrated rate law is focusing on time. We are going to stick with the differential rate law, so the rate equals K times the concentration, not the integrated version, because you do need calculus in order to use the integrated rate law. So IB is just using the differential one, but a heads up, if you are self-studying for an AP test, they would also include the integrated rate law. The next thing that I want to talk about is the units for the rate constant K. So I want to pick up with the reaction rate law that we determined in the last video. So the answer here was that the rate is equal to 4 times 10 to the negative third times the concentration of A squared. But we can actually determine the units for this K by looking at the units for the components of the reaction, or of the equation. So first, if we look at the number on top, that would be the rate on top, and the units for the rate given are molarity per second. Next, we're going to look at the bottom where we have the concentration of A, which concentration brackets is always going to be molarity, but it's actually squared according to this rate law. So on the bottom we have molarity squared. Now we need to simplify this unit. So to simplify this, we're going to need to use our reciprocal, which you can put anything over 1. So we flip that around. This is what we're looking at now. Molarity over second times 1 over molarity squared. And of course, one of the molarities will cancel, basically leaving us with 1 over second times molarity, or inverse seconds and inverse molarity. The thing is, we're still not done, because we know that IB doesn't like to leave molarity as their unit for concentration. They prefer to think of it as moles per decimeter cubed. So if we think about it that way, we need to kind of unpack this a little bit, because now we have a fraction in a fraction. So now if we think reciprocal again, we can bring the decimeters cubed to the top and put that over seconds and moles. And this would be a little bit more simple. But of course, we want to kind of IB-ify our units and bring the things that are in the bottom up with the -1 exponent. So this would be our final IB style unit here. dm to the third, mole to the -1, and second to the -1. Before we dig into another example, let's take a step back and look at the big picture. Why do we care about the reaction rate law? What does it actually help us do? And the point is that it's going to help us kind of predict how the reaction proceeds. Is it going to have a constant half-life, or is that going to change? How quickly is my reactant going to be used up? And that all has to do with whether it's a first, second, or third order reaction, or a 0th order reaction. This graph is hopefully a familiar example, something related to radioactive decay or nuclear reactions. And in this first order reaction, we have a constant half-life. But that can change if the reaction is more or less dependent on the concentration. So here's a very common example of carbon dating, looking at the carbon-14 decay, where you see this constant half-life. After the same exact half-life, you have exactly half the material left. So it is very useful to know how to calculate exactly what the reaction orders are and what exactly K is with the proper units, but you can also make some predictions just by comparing the data if you know what to look for, and this can really help you save a lot of time on something like a timed IB exam. So for this next example, we're going to inspect this data given for the reaction of hydrogen gas with a nitrogen monoxide. And we're producing water and the nitrogen gas, and you see the different concentrations changing and producing these different rates. So let's start with what it means to have a first order reaction. If you have a first order reaction, your concentration is directly proportional to your rate. Meaning if you double one, you double the other. If you triple one, you triple the other. So doubling the concentration makes it happen twice as fast. Now if you have a second order reaction, then that is a little bit more of an effect. So say I have the concentration and I double that, then what that's going to do is quadruple the rate. So it's like an exponential relationship. On the other hand, if you have a zeroth order reaction, that means that the concentration has no effect whatsoever on the rate. No change whatsoever on the rate from changing the concentration. No effect, zeroth order. So now let's look back at this reaction between the hydrogen gas and the nitrogen monoxide and try to predict our rate law without doing the calculation. So first, if we look at the reaction with respect to the hydrogen gas, we would like to compare experiments where there is a change in the hydrogen gas concentration, but not in the nitrogen monoxide concentration. So that way we know the effect on the rate is specifically caused by only the changes in the hydrogen gas concentration. What we see in the concentrations is that they are doubled. We see the same exact thing in the rates, doubled. So if both reactions, if both the concentration and the rate is a double, that would indicate a linear relationship or a first order reaction. So that tells me that M, or the order of the reaction with respect to hydrogen gas, is 1, showing that first order reaction for our first reactant. Now let's try to predict based on the nitrogen monoxide concentration, this one. So here I want to make sure that the nitrogen monoxide concentration is changing, but not changing the hydrogen concentration. So that would be experiments 3 and 4 to compare, to see how nitrogen monoxide concentration affects the rate, not the hydrogen. So here we see that the concentration also doubles, but the rate actually doesn't double, it quadruples. So if we double the concentration and get 4 times faster of a reaction, that's an exponential relationship, or where the concentration is equal to the rate, or proportional to the rate squared. And so that would indicate a second order reaction. Now be very careful if this is an IB free response question, because you do need to either show the calculation or explain in words how we are assuming these answers. So you would need to describe doubling the concentration produced 4 times the rate and show that indicating the second order reaction. Or back on the hydrogen gas, show that doubling the concentration produces twice the rate, showing that linear relationship. Explain that in words is just as good as calculating it. So now that we have figured out the reaction order with respect to hydrogen is 1, we can use the 1 for M, and since N is 2, we can plug that in as well, and we have our rate law just missing K. So that would be the next step. There really is no way around calculating K. You're going to have to figure out your M and your N one way or the other so you can get to this part of the rate law with the correct exponents. But from here we need to plug in values for K, and just like when we did the easier one earlier, it does not matter which experiment you picked. So here I've just narrowed it down to the first experiment, and we're going to plug in the values for the first experiment for everything except for the constant K, and we'll solve for that. But this time I want to do it with the units along the way. First thing I'm going to do is to plug in the rate with the units of moles per decimeter cubed per second on the left side of the equation, where it says rate equals. The next thing that I'm going to do is plug in the concentration for the hydrogen for this H2 concentration using the moles per decimeter cubed units, and the exponent is just 1. And then finally, I'll plug in the nitrogen monoxide concentration with those same concentration units for this section, but here the exponent is 2. And that square is going to affect the units as well. So I'm going to start on the right by consolidating this section. So if I start with the math and multiply 1 times 10 to the negative third by 6 times 3 to the negative third squared, we get 3.6 times 10 to the negative eighth. Let's think about what's happening to the units. First, I have mole squared, and then times another mole is going to make that mole to the third. Next, I have decimeters to the negative third squared is going to make that decimeters to the negative sixth, and then times another negative 3 is going to make that decimeters to the negative ninth. So that's what I've got on the right hand side so far. Still all of this times K set equal to our rate. So now, in order to isolate K, I'm going to take my rate and divide it by that number I just got. So first of all, numerically, 3 times 10 to the negative third divided by 3.6 times 10 to the negative eighth gives us 8.3 repeating times 10 to the fourth. But since some of our initial data only had one significant figure, we're going to round that to 8 times 10 to the fourth. The hard part is the units. So let's start off easy. On top I have 1 mole, and on the bottom I have 3 moles. So one of those will cancel, leaving mole squared on the bottom. Now if you look at the decimeters, we have a negative 3 on the top and a negative 9 on the bottom. So that actually simplifies, negative 3 of them being gone, leaving a negative 6. And you can look at the reciprocal of this to make that make a little more sense. 3 of them are canceling from the same position, the denominator of the numerator and the denominator of the denominator. So they cancel 3 for 3 in that position, in the negative position. So that's mole squared and dm to the negative 6, and then nothing cancels with this s to the negative 1. So what's left on top is s to the negative 1, and what's left on the bottom is a mole squared and a decimeter to the negative sixth. The thing is, we can't leave it like this, having negatives in both the top and the bottom. We kind of need to flip this out and figure out what that means. So now it really helps to think about this more as fractions. So s to the negative 1 is actually 1 over s, and then mole squared dm to the negative 3 would mean mole square on top and decimeter, sorry, not negative 3, negative 6, so this will be positive 6 if we actually write it in the denominator. So now if we use the reciprocal on this part, we get 1 over second times the decimeter to the sixth, that's a 6 I promise, and then mole squared on the bottom, doing the reciprocal of the denominator. And so back in more normal terms, we have a decimeter to the sixth on top, and we have second and mole squared on the bottom, which we can now write as decimeter to the positive sixth, mole to the negative 2, and s to the negative 1. And that would be our final actual IB style unit for this rate constant. So here we are finally at our 1 sig fig of 8 times 10 to the fourth, decimeter to the positive 6, mole to the negative second, and negative second power, and then second to the negative first power. Okay, I know that was a lot, so feel free to pause the video and take a quick break. We're going to move on to looking at a completely different thing, looking at the graphical representation of reaction kinetics. So we're going to look at what it actually means to be first order, second order, or zeroth order. So first we're going to start off with 0th order. Here we basically have the exponent being 0, hence the 0th order, because the exponents are the orders of the reaction with respect to that reactant. And if it's 0, anything to the 0th power is just 1. So essentially what we're saying is the rate is equal to the rate constant. And so that means that the concentration does not affect the rate at all. And so you see just this plateau, zero-sloped line. But then if we look at the concentration as an effect of time, well, the reaction's still going to proceed, but just in a linear fashion. So this shows that the reaction does progress, but not as a function of concentration. Now let's look at a first order reaction, where the exponent would just be 1, and anything to the first power is itself. So we don't need to write that, and we just write rate equals K times the concentration. And what this is showing me is that rate is proportional to the concentration of the reactants. So, or of this case, this is one reactant, reactant A. And so when we look at this changing concentration, as the concentration is increasing, my rate is increasing. And it's doing so in a direct proportion. And so you see rise over run being very consistent here, this linear increase of rate as a function of concentration. And so what happens if you look at this as a function of time, where concentration depends on time, you're basically getting this exponential decay, where as I'm decreasing and decreasing my concentration, it's taking longer and longer time. Or probably a better way to say it is as time progresses, the concentration's changing less and less often. And this is what you really see with nuclear decay. At first you start off with 100 grams and then you get to 50 grams, but then 25, and then 12.5. And eventually you're barely changing at all, even though you're still going through a constant half-life. So this shows that rate is directly proportional to concentration and experiences exponential decay over time. Finally, let's look at a second order of reaction. This was where if I doubled the concentration, I quadrupled the rate. And so you're seeing kind of an increase, exponential growth in the rate as concentration is increased. And that's because it is even more dependent on the concentration. What happens is as we go over time, the concentration really depends on the time. And so we actually get uneven half-lives because of this huge dependency on concentration. So this basically shows that an exponential growth in the rate's relationship to concentration produces an even more exponential decay on the concentration's relationship to time. So these are all very important graphs. You should be able to identify which order reaction you have based on the shape of either of the graphs, rate as a function of concentration or concentration as a function of time. All right, the last thing that I want to do with these notes is to look at the application side of this, maybe exponential decay, and how that can kind of give us an indication of what's going on in the sense of how long it takes for a reaction to occur. And so one of the best examples is half-life. So there is a relationship between the reaction rate constant K and the half-life of a reaction. And so this formula is in the IB data booklet. The half-life is equal to 0.693 over K. Again, if you're self-studying for the AP test, you may want to look into where this equation comes from, but IB gives it to you. So one thing you may not have known is when we first learned about half-life, we really only looked at first-order reactions. We assumed that the half-life was always constant. You have 100 milligrams of something, it goes through one half-life, you have 50 left. The second half-life, now it's 25. And so over the same amount of time, we're getting half of the substance left. And that's kind of the premise we used for half-life. But the fact actually is that that really only works if it is a first-order reaction, because that's how first-order decay works. If it were a second-order reaction, that would be a much steeper curve. And so the truth is that half-life is not necessarily constant, or it's actually not constant if it's a second order reaction. Now let's look at these graphs for a 0th order, 1st order, and 2nd order reaction. So I'm going to actually start with the 1st order reaction, which is our typical interpretation of half-life. It's how most things work with a nuclear decay. Each half-life is the exact same amount of time, looking at time versus concentration, or I should say concentration as a function of time. You get the same exact half-life, producing literally half the substance. Now, if we increase the dependency on concentration, so increasing the concentration on the left, what we see is a steeper drop in the beginning. And so the first half-life is very short, but then it takes longer and longer the more we decrease the concentration, because we're so dependent on the concentration. Every change in concentration produces twice the effect on the time it takes. And so you're going to get more and more of an effect on the half-life. Every time we drop the concentration, that half-life extends. On the flip side, if we have a 0th order reaction where the concentration does not affect the rate at all, then we're just continuing to progress linearly the relationship between the time and the concentration. And so you actually start off with very long half-lives, and they get shorter and shorter because you have this constant slope of the reaction. So there is a trend here, and you can actually tell by comparing half-lives what order the reaction is. If the half-life decreases with concentration, that's because it doesn't really depend on concentration, hence the 0th order. If the concentration produces a constant half-life, that's because there's a linear relationship or a 1st order reaction between the two. And then as we increase our dependency on concentration, we're increasing our half-life with our 2nd order reaction. So this shows how you increase your dependency on concentration, you affect the rate or time more and more. So I'll get into some of these examples in just a minute, but I want to really focus on a big trend here. The shorter the value of the half-life, the faster the reaction. So a long half-life would represent that the reaction is happening very slowly, whereas a short half-life would represent that the reaction is happening very quickly. Half-life doesn't have to be literal. So I once had someone ask me if they could shorten the half-life because they didn't believe the world existed for as long as some of these half-lives. That really just shows that they didn't understand what half-life means. I don't care whether you believe the world existed this long or not. The value of the half-life is actually a representation of the rate of the reaction. And you have to be very careful because there is a different relationship with rate as opposed to time. And half-lives are typically given in units of time, right? How long it takes for half the stuff to decay. But you should also need to be able to look at these half-lives and make an inference into the rate of the reaction. And again, it's inversely proportional. A long time means a slow rate, and a short time means a fast rate. Next, I want to point out a few of these isotopes that we have seen before and that are kind of important. So plutonium is a very common nuclear fuel. It actually has to do more with the fact that it's very low penetration, which makes it a little bit safer, and it does have a generally long half-life. We've also talked about radium-226, which was used to treat like brain cancer, where you could do radiation for brain cancer, and that has a very long half-life. And so the only way to get very effective treatment from the radium was to pinpoint where those rays, gamma rays, were being pointed and get them to intersect only on a brain tumor, for example. Another one we've talked about is the iodine-131. So this is kind of an important one that has a very short half-life, and that's because people actually ingest it in order for it to work. We call it a medical tracer. And so it emits radiation that we can track, but it's gone more or less to negligible quantities very quickly because its half-life is only 8 days. Now let's tie this back to kinetics. Since radioactive decay typically follows first order rules, that was where the reaction half-life was constant and not hugely dependent on concentration, not dependent on concentration, 0th order, but directly proportional. And so that's why the half-life is able to stay constant, and that's why we're able to predict with pretty accurate results how these things will decay and how the half-life is able to give us so much information on the rate. So just to tie it back again to a very important real-life example, iodine-131 was one of the isotopes that had a very short half-life. If you remember, it was 8 days. And so you see this constant half-life showing that over a very short period of time, we have negligible amounts, almost 0, left to be able to be detected in the body. So that makes it very good for diagnosis, especially of identifying thyroid cancer. And then in terms of treatment, it allows you to kind of see where things are being affected, where things are slowing down. So it's very useful that it has a short half-life because it makes it actually pretty safe to use, even literally eating and ingesting the iodine tablets. Alright guys, that'll do it for the end of Unit 6 Notes B. The next set of notes, Unit 6 Notes C, will be all about reaction mechanisms and activation energy. See you there.